Have you ever thought about how machines make predictions better than us? If not, be ready to be amazed by the math that goes behind one of the easiest machine learning methods, linear regression with one variable. In machine learning, there are two methods. Unsupervised learning uses unlabeled data to train the model, and the model finds patterns itself. Supervised learning uses labeled data to train the model. In other words, we give the correct answer to the model so that it can predict the correct answer for another value that it hasn't seen before. Supervised learning is used in two types of problems, regression and classification. In this video, we will talk about linear regression with one variable. Let's look at house sizes and their prices. Our model will come up with a linear function h that maps the sizes, which are the x variables, with prices, the y variables. We can write the h function as hx equals theta 1 times x plus theta 0. So how will our model find the theta values? Say the best fit line of this plot is like this. The idea is to minimize the sum of the distances between the real values and their predicted ones on the best fit line. We do that by using the cost function. In our dataset, there are m different xy couples, and xi, yi denote the ith couple. We denote the cost function as j theta 0 theta 1. To minimize the sum of distances, we need to minimize the cost function because the cost function is defined as the sum of the squares of the distances between real values and predicted values divided by 2m. To do that, let's first take a look at the 3D plot of the cost function with respect to theta 0 and theta 1. As you can see, the bottom of this bowl-shaped plot is where the cost function gets its minimum value. In linear regression with one variable, the 3D plot of the cost functions is always bowl-shaped, so we are sure that there is only one minimum for the cost function. If you look at the function from above, we see something like this. Similarly, the minimum value of the cost function is in the middle of these ellipses. We'll reach that point with gradient descent. The algorithm is simple. You start with random thetas, then you simultaneously update both of them with these expressions, and you repeat this until convergence, meaning that at some point, theta 0 and theta 1 do not change when you update them again. Here, the term next to the alpha is basically the derivative of the cost function with respect to theta 0 and theta 1. Alpha is the learning rate, meaning the measure of our steps. Look at these two plots where we only compare cost function with theta 1. For simplicity, we took theta 0 as 0. If the learning rate is too small, it can take too long for our model to reach the optimum cost function value. If the learning rate is too large, it may not converge to the minimum value of the cost function and may even diverge. To conclude, with the optimal value of alpha, our model will reach the minimum value of the cost function and thus find the right values for theta 0 and theta 1 to form a linear function for the best fit line for our dataset. Let's look at an example. Here, the model will predict a linear relationship between city populations and the profit made by the food truck chain in those cities. You can see the best fit line here, and we have made two predictions. For a city with 35,000 population, the predicted profit is about $4,500, and for a city with 70,000 population, the predicted profit is about $45,000. And this concludes our quick intro to linear regression. Now you know how our artificial friends work.